Okay, hi. Today we shall be developing a regression model, and we have three variable. One is price of the product, then income of the consumer, that is our second variable, and the third variable, cost for ad. We have these three variable, and our data is cross-sectional in nature. So meaning that problem of serial correlation may not appear. So we shall not be checking serial correlation for this model because our data is cross-sectional in nature. So normally serial correlation occur in time series data, not cross-sectional data. And the question is that what are our variables? You can see our variables are here. These are our variables: income of the consumer, price of the product, and the cost for ad. This is our three variables, and you can see the sample size is 30, and the data we have collected today, so that is why the data is cross-sectional in nature. Okay, we can run the model now, analyze the regression linear, right? And here the price is the dependent variable. I take it here. Then income and ad are the independent variable. So I take it here. And here our task is whether income can influence price or not, or whether ad can influence price or not. That is our target. And here are many methods. Out of many methods, I choose entire method, meaning that all the variables will be participating to estimate our model. When I choose this entire method, all the variables will be participating to estimate our model. Okay, then it is set. Then I go to the statistics, this part, statistics, and here I choose estimate to coefficient estimate. I choose it. Then model fit, that means whether the model has been fitted or not, meaning that whether the data has been fitted or not. And there is a residual. This is called Durbin-Watson statistics. Normally when we check the serial correlation, then we select Durbin-Watson statistics. But here our plan is not to check the serial correlation because our data is cross-sectional type. So we are not selecting Durbin-Watson statistics. But if the data is time series type, then we can select Durbin-Watson statistics. Normally serial correlation occur in the time series data, not cross-sectional data. Normally it happens like that. Okay, then I proceed, continue. Okay, then I go to plot. Okay, this one is the y axis, and this one is the we call it there are two things. One is y axis and one is x axis, right? We have two axes. So here what we are doing here now, in the y axis I am putting z receipt, and in the x I put z spread. Okay, what does mean by this z receipt? Meaning that standardized residual that we have derived from our estimated model. So I'm telling again, this one is the standardized residual in the y-axis. And what about this one? It is called standardized predicted value of the dependent variable, meaning that standard predicted value of the dependent variable, which is price. So here price is our dependent variable, and we shall be estimating or predicting our dependent variable, which is price. Okay, so from this plotting we shall be checking whether we have heteroscedasticity or not, and heteroscedasticity is not desirable. Okay, then I proceed, continue. Then I go to shape. Okay, here is the shape, linear model shape, you can see. And here is the residuals, right? So there are 1, 2, 3, 4, 5 types of residual. Out of 5 types, I choose this one, standardized residuals. Why? To check whether the residual is normally distributed or not. That we want to check, and that is why we are saving this standard residual to check whether the residual is normally distributed or not. And for a good model, residual should be normally distributed, and that is always desirable. Okay, so I continue with our model. Okay, the model is ready for running. So I click OK. The result is coming up. So gradually, my computer is very slow, so normally it takes some time to come up the result. It is coming gradually. You just wait a few seconds. It has come up very nicely. Okay, first I talk about model summary, right? This I make it big so that you can see better. I make it big. Table properties. I go to sorry. Okay, what am no, sorry, I've done a mistake. Just 1 minute. I make it big. Cell properties, not table properties. Okay, I choose 16, right? It is big now. Okay, here you can see the value of r square is how much? The value of r square is 88.2%. right? It is 88.2%. What does mean by 88.2%? That I can explain now. Here is the R squared is how much? R squared is 88.2%, right? That is our result. And we have three variables. Price is the dependent variable, and income and add are the independent variable. Okay, then I can say 100% minus 88.2%. So the value is around 12%, right? Okay. So what is meaning by this 88.2%? That is R squared. So the meaning it 88.2% fluctuation in price can be explained by our two variables such as income and add. So meaning that income and add can contribute 88.2% fluctuation of price. Okay, then what about this 12%, which is 100% minus 88.2%? Here 12% is the approx value, not exact, approx value. Okay, so what is this 12%? It means that 12% fluctuation in price can be explained by other variables which are not included in our model, meaning that outside factors, meaning that 12% fluctuation of price can be explained by other factors outside our model. That means 12%, which is 100% minus 88.2%. Okay, here what does it means? What is the summary? Summary is outside factor influence only 12% our dependent variable. That means the variables which are outside our model can influence very small on the dependent variable, which is price, meaning that our model is very nicely fitted. So normally we say when the value of R squared is more than 60%, when the value of R squared is more than 60%, then we say normally our model is nicely fitted, meaning that higher the R squared, better the fitted of the model. That is the always guideline. Okay, so we are happy about the model because R squared is very high. Okay, then we check about analysis of variance, which is ANOVA. I make it big for you so that you can see better. Cell properties, I choose 16. Okay, it is like that, ANOVA analysis, and it is the F statistics and corresponding significant value or p value. And normally if the significant value is less than 5%, then we say the corresponding statistics is significant. So here the significant value is almost 0%, meaning that F statistics is significant, meaning that our two variable, those are ad and income, are significant jointly to explain our dependent variable, which is price, meaning that ad and income are jointly significant to explain price. So we are happy about this model because here R square is quite big and F statistics is significant, so we are happy so far. Okay, then we check about our coefficient, whether coefficient are significant or not. I make it big, cell properties, I take it 16, right? It is so big now. Okay, we have two variables, one is income, one is ad. Okay, first I check the income. I go to significant value or probability value or p value. Normally when the significant value is less than 5%, then that particular variable becomes significant. Okay, here the income, for this variable income, significant value is very small, almost 0, meaning that income is a significant variable to explain price. Okay, then what about the ad? This variable, the significant value is 13.7%, 13.7%, which is more than 5%, meaning that our ad is not a significant variable to explain the price because the probability value is more than 5%. So out of these two, at least one is significant, that is the income. So we are happy about this model. Normally, what is the guideline? The guideline is if most of the variables are significant, we can accept the model. And here, out of two, at least 50% have been significant. So we are happy about our model. Okay, then we check whether our model has heteroscedasticity or not. That we want to check. And we can check it here. I make it small for you so that you can see better. I make it small. It is become I make it some small. Okay, make it small for you. Just 1 minute. Okay, it is becoming small. Just 1 minute. Now it has become small. You can see now, right? I guess so. I see better, right? Okay. So here you can see that is called Scatterplot. We can call it Scatterplot. This one, right? Scatterplot, and price is the dependent variable. And this side is standardized residual, meaning that Z receipt, right? This side is Z receipt, and this side is standard predicted value, meaning that Z pred. So last time, can you remember, we we created two variable. One is Z receipt and one is Z pred, right? So this is in the y axis. This is in the this is in the y y axis, and Z pred in the x, right? That we set last time, right? And the whole thing is here. You can say this one Z pred and this one Z receipt, and these are the residual plotting. So here you can see the residual is going down, then going up, then again going down. So I suspect that probably in this model there is heteroscedasticity, because the residual has a sequence. So here you see it is going down, all the residuals are going down and going up together, again going down. So normally when there is a sequence when there is a sequence like this, then normally we say there is a heteroscedasticity, and that is not desirable. Okay, so so further we can check about it, such as this one. I can show you better from example. Suppose this one, right? Okay, this side is the Z receipt in the y axis, and this side is the Z pred, and these are the residual. Okay, suppose if the residual plot like this, you see from here you can see one thing, they are going up, going down and going up. That means there is a sequence, right? And when this thing happen, there may have heteroscedasticity. And also like that, suppose if it is like this, it is going up and going down, there is a sequence, meaning that we have the problem of heteroscedasticity. And it can be also like that, you can see. You see, these are going up, right? Both sides are increasing, right? Both sides are making big. And when the residual plotting like this, then we can say there is heteroscedasticity. So that is not also desirable. But when the residual plot like this, here you can see, when the plot like this, you see there is no sequence. That means each and every residual is independent. That means no one is following each other. They are random. That means there is no sequence. there is no specific direction. All the residuals are independent. And when this thing happen, then we can say there is no heteroscedasticity, and that is desirable for a model. Okay, and we see our model. We go back to our model. What is happening here? Here the residuals, all residual are going down and again going up and again going down. So we can say that uh, this model has heteroscedasticity. Okay, now the question is that how to remove the heteroscedasticity. How to remove it? One way is the logarithm transformation. Logarithm transformation to remove heteroscedasticity, meaning that we shall convert all variables into log, and then we shall estimate the model again, and probably the heteroscedasticity problem will be removed. Actually, there are many ways to remove the heteroscedasticity, but one way is logarithm transformation out of many ways. So here what is our plan? We shall convert all our variables into log, and then we shall estimate again, and that is called logarithm transformations. Okay, so and we have and and we shall be checking now, that is the last checking, whether our residual is normally distributed or not. That we want to check, and then after checking this one, we shall convert all the variables into log, and then we shall estimate the model again. Okay, now we check whether residual is normally distributed or not. And last time we saved standardized residual, right? Can you remember? Last time we save it. Okay, last time we saved standard residual, and we can use this residual to check whether our residual is normally distributed or not. Okay, how to check? Okay, so what I do, okay, this time I go to analyze, then I go to descriptive statistics, then I choose the explore, right? Okay, you see, so there are now, this is one variable, standard residual. Last time we saved it, and it is here. I bring it here, and it is under explore. Make sure we have to choose the explore. Okay, then I choose the plot, then I choose this one, not this one, I choose this one, and I choose this one, normality plots with test, right? This one, I choose this one to check. I continue, then OK. So the result is coming up gradually. Okay, this is the first result, test of normality, whether the residual is normally distributed or not. Okay, there are two approach. Normally there are two approach. One is to approach normally. One is to approach test of normality. Okay, there are two approach. One is mathematical approach, and the second approach is the graphical approach, right? And there are two approach, and mathematical approach can confirm the result all the time, right? So meaning that out of these two approach, mathematical approach can make the result confirm whether the residual is normally distributed or not. But the graphical approach cannot confirm the result, right? Okay, so first of all, I talk about mathematical approach, right? And it is here. You can see we have two approach. One is, okay, I make it big for you. I make it 16, right? You can see better. 16. Okay. Okay, here is two approach. This is standard residual, right? And this one is a variable, right? Now the residual has become a variable. Okay, two tests. One is Kolmogorov and Shapiro. It is the statistics corresponding significant value or probability value or p-value. And what is our null hypothesis and what is alternative hypothesis? Our null is residuals are normally distributed, and that is desirable. And alternative is residuals are not normally distributed, and that is not desirable. So null is desirable. The residuals are normally distributed. Okay, and here you can see the significant value is very small, less than 5%, meaning that we can reject the null hypothesis and can accept the alternative hypothesis, meaning that the residuals are not normally distributed, so it is not desirable. Okay, then we have the second test, Shapiro test. You can see the significant value is 2.2%, 2.2%, which is less than 5%, meaning that we can reject the null hypothesis, meaning that residuals are not normally distributed. So what is happening here? So here both test is telling the same thing. Both mathematical test is telling that residuals are not normally distributed and which is not desirable. Okay, now we check the graphical approach, right? From here I go down. So this is the first graphical approach. You can see from here I can make it for you. It's so big, right? It is so big, and we call it okay. Here the plotting, right? We call this one histogram. So here this side is the residual, standard residual, and here you can see the plotting is not normal, right? The plotting is not normal. So this one is the graphical approach, and the graphical approach is telling the same thing, that residual is not normally distributed. And we can also check some more graphical approach, such as here. Okay, so what is the guideline? This one is a straight line. So and we can call it normal QQ plot of standard residual. And what is the guideline? When this circle, right, are falling on this line, then we can say that particular variable is normally distributed. But here you can see this circle is slightly away. These circles are not falling on this line, so we can say that our residual is not normally distributed. Okay, finally we check the last one, the graphical approach again. So we can call it box plot, right? It is the residual, right? And it is the median value. And normally when the median value in the center, it is here, then we can say that residuals are normally distributed. But here this we call it median. Median is not in the center, so we can say that residuals are not normally distributed. Okay, what is the guideline normally? The guideline is actually, normally we say that when the median is close to top, meaning that that particular variable is negatively skewed. And again, when this median is close to bottom, then we say that that particular plotting is positively skewed. But when this median is in the center, then that particular variable is normally distributed. Okay, and here what is our decision? Our decision is that mathematical approach and graphical approach is telling that residuals residuals are not normal, and that is not desirable. Okay, and our model actually has two problems. Number one problem, our model has the problem of heteroscedasticity, and the second problem is that residuals are not normal. Okay, so to solve this problem, so I better go for logarithm transformation, right? And then I estimate the model again, meaning that I convert all variables into log, then I run it. Okay, so I proceed with this one. Okay, what I do, okay, how to convert variables into log. I just come here, I go to transform. You can see from here, transform the variable. I click on it, just 1 minute, transform, then I choose compute variable, right? I choose it, so the result has come up. You can see compute variable, right? And here you can see all. Okay, I choose all here, I click on the all. After clicking, I can see the, I am looking for log ln, right? Can you see ln? I click ln. Okay, then it has come here, right? Okay, so I have three variable. One is income, price, and ad. Okay, the first I choose the target variable. I like it log income, L income, meaning that log income. Log income means L income, so that is the name of the new variable. And here I put our variable income, right? So so I can make it zoom for you. You see here. So the target variable is L income. I have given a name, and here I put ln income. Now a new variable will be creating, and that is called L income. That means our income variable shall be changed to log income. That will happen now. Okay, so here I press OK. I press OK. Okay, so the variable has been converted to log. Okay, no, but I have another two variable. So I go again, compute variable. Okay, then here I do, last time I did log income, now I do log price, right? Log price, and here I put price. I put price, then I press here OK. Okay, then I have one more variable, and that is add, right? So I give it L add, meaning that log add, and here I put add, right? I put log add. So I can make it zoom for you. You can see it is log add, and here I put ln add, and you can see we have two new variable, log income and log price, and now log add will be coming here also. Okay, then I press OK. Okay, now all the variables have been converted to log, and we can estimate the model again to remove the problem of heteroscedasticity, and also to make the residual normal. Okay, I go to analyze. I choose regression linear. Okay, here is the things. Okay, here you see, so the dependent variable should be log price. I take it here. Then we have two variable such as income, log income and log add would be independent variable, right? So these are our two new variable, and I choose the same method, enter method. Then I go to statistics. Then I choose estimate and for model fit. Then I continue. Then I go to plot. Then here I put Z receipt as before, and here I put Z spread as before, right? So this one, then I continue as before. Then I go to save as before. Then the residual, I choose standard residual. Okay, standard residual from the model, from the log variable model. This time variables are log. So the we are getting standard residual from log variable. Okay, then everything is set. Then I go to continue. Okay, it is set now, right? Then I click OK. So result is coming up. Okay, so first is our model summary. You can see I make it big for you. One minute. Okay, I make it big. I make it cell properties 16. Okay. Okay, here you can see we have two independent variable, and those are log variable, and our dependent variable is also log. Okay, here what is the value of r square? R square value is also quite high. It is 74.9%. So we are happy about the model. So that means the model is nicely fitted. And what about ANOVA? Okay, but our previous r square was how much? Our previous r square was 88.2%, but now the value of r square become how much? 74.9. So they are almost close to each other, right? So not the gap is not that big, and 74.9% is quite good. We can accept the model very happily. Then I check the ANOVA. What is happening here? I make it big for you. So here the F statistics is also significant, meaning that log add and log income jointly can influence our dependent variable, which is price. So we are happy about this model. Then I check the coefficient. I make it big for you. Okay, so what is happening here? Log income is significant because the significant value is less than 5%, but the log add is not significant because probability value is 38.9%, which is more than 5%, so it is not significant. But out of these two variables, at least one is significant, so we are happy about this model. Okay, then finally we check whether our model has heteroscedasticity or not. That we check. Okay, big. I make it small. Just 1 minute. Okay, here we can see that. Okay, this is the dependent variable log price, and this side is Z receipt, standard residual, and this side is standard predicted value, that is Z pred, and these are the plotting of residual. And what is happening here? The residuals are going down jointly, then again come up, and they have a sequence. They have a particular sequence, or they have a particular direction, meaning that the heteroscedasticity problem is still there, although we have converted the variables into log, but the problem of heteroscedasticity is still there, so we are not happy about the model, right? Okay, then we check whether the residual is normally distributed or not. We check now. So we go to analyze, then go to statistics, then I choose the explore, right? I choose explore. Okay, so I make it reset. Okay, now actually there are two residual, and this residual has no log, but this residual has log, right? So meaning that this residual we have taken after converting the variable into log. So here I shall select this residual to here, right? And then I shall choose the plot, then I choose histogram, not this one, then I choose normality plot with test, then I continue, then I okay. Okay, the result is coming up. Okay, so first I check the, because we have two approach, one is mathematical approach and one is graphical approach. Okay, the first is the mathematical approach. I make it big for you so that you can see better. Cell properties, I make it 16, right? Okay, it has become big. It is the standard residual, and we have that test 1, test 2, and here you can see and what is our null hypothesis? The null is residuals are normally distributed, and what is alternative hypothesis? Residuals are not normally distributed. Okay, this is our first test outcome. The significant value is 9.5%, meaning that we cannot reject the null hypothesis, meaning that residuals are normally distributed. So we are happy about it, because after converting all the variables into log, the residual has become normally distributed. Okay, but the second test is the probability is 3.9%, meaning that we can reject the null hypothesis, meaning that we can accept the alternative hypothesis, meaning that residuals are not normally distributed. Okay, now the question is that so here the first test residual is normally distributed, and here residual is not normally distributed. Now it is up to you to decide uh, which result you will accept, this result or this result. It is up to you now. You decide which test is your benchmark to decide. So it is up to you now. So okay, suppose I choose this result. Suppose I choose this test as a benchmark. Suppose I choose this test is a benchmark, then I can say that our residuals are normally distributed after converting all the variables into log. Okay, that is, and also you can check the graphical approach. We have the graphical approach here also. I can make it small. Just 1 minute. The graphical approach, and from this approach we can see that residuals are not normally distributed, you can say, but from here it is very difficult to say, because but you say whether the residual is normally distributed or not, it is very difficult to say, but from here we can see probably residual is not normally distributed, because it is not normal, right? Okay, then we can check other graphical approach. From here we can also say that you can see that all the circles are not falling on this line, but they are very close to this line, right? Meaning that we can say from this table, from this diagram, the residuals are normally distributed. And finally, you can check the box plot. We can check the box plot. According to the box plot, okay, according to this box, you can see the median that is here, right? It is not in the center, right? Meaning that residual is not normally distributed. So that is a graphical approach result. But now it is up to you to decide whether the residual is normally distributed or not. But we always depend on the mathematical approach to take a decision. And suppose this test is my benchmark, then I can say our residual has become normal after logarithm transformation.